Now the physical layer, if you remember, it was the last layer on the TCP/IP model or the OSI model also. The physical layer is the one responsible of sending the data and receiving the data. And it's the one directly connected to the transmission media or the transmission medium, like where you send the data. So there are many ways to send the data. It could be through wires, it could be through wireless. You can send them in analog, you can send them in digital, and so on and so on. So the outline for this lecture, for the media, we have two types or two categories. So we have guided media and you have unguided media. Guided media means that there is a physical device that the signal goes through it. So it's a wire or a cable. Then we have three types of guided media. We have twisted pairs, coaxial cable, and fiber optics. Each one of them has an advantage over the other. The most widely used ones are twisted pairs and fiber optics. Coaxial cable, it's more into TV cables, like satellite TV cables, like it's an old tradition. But nowadays, I think everybody's moving into fiber optics. But we still have many applications that use the twisted pairs. I'm going to give you examples on each one of them. And I will, let's say, highlight the key components on each one of them. Then we have the unguided media. Unguided media means that you have the space. Like there is no physical device to touch. There is like the signal is everywhere. So it's not that if you cut a wire, you lose the signal. Here, the signal travels through air or through space. So we have radio waves, microwaves, and infrared. Radio waves and microwaves, usually they are categorized together. Just each one of them has a different application over the other. And there are limitations for each one of them. And then we will have the transmission media. Okay, this will hide. Let me just hide this one. Okay. Transmission medium, the transmission here, like the way you send the signal. So there are three different technologies. There is time division multiplexing or time division multiple access, frequency division multiplexing, or frequency division multiple access. Each one of them has an abbreviation, TDMA, time division multiple access, or FDMA, frequency division multiple access, and code division multiple access. And it's about like this part here is only about 4 to 5 slides. I did not go into deep technical aspects on this topic. It's going to take forever if we start the technical part of this one. I just want to tell you what is the difference between one and the other. All right, so why is it important to talk about the transmission media or the physical layer? Well, think about it this way. Now we are limited in wires. Like you'll see the network, you'll see a wire that is common in many networks. So how can multiple hosts communicate over the same wire at the same time? Definitely, if you send the signals at the same time, there will be collision, like there will be interference between the signals, each signal and the other. So how to manage that? And how much bandwidth can I get out of specific transmission medium? If you send over twisted pair, you are limited by a certain frequency or bandwidth. If you send over fiber optics, you will get probably more bandwidth than twisted pair. So the change of device material or the medium material, you can get higher bandwidth. Now, what are the limitations when it comes to the physical size of the network? Now, imagine for each connection, you need a wire. So basically, you'll end up having a lot of wires, and that will be impractical at all. And how do the properties of copper, fiber, and wireless compare? Which one you prefer over the other? Definitely nowadays, everybody prefer the wireless. You don't have to worry about physical wires and connections and cut in the wire and so on. But it's going to be more complicated technology when compared to the fiber and copper. All right, so this is like an idea why it is important to study these parts. Okay, so before we go into them, let's say the body of the topic, there are many standards that covered these transmission media and like the hardware associated with the networks. So the physical layer hardware or media encoding and signaling standards, they are defined and governed by these standards organizations. Now look how many organizations are in there, like there are about 7. So we have the International Organization of Standards, that's ISO. Anything related to standards, ISO will be there. Now there is the Telecommunications Industry Association or Electronics Industry Association, TIA and EIA. So this one is also responsible at some point. International Telecommunications Union, American National Standards Institute, Institute of Electrical and Electronics Engineers, National Telecommunication Regulatory Authority, including the Federal Communication Commission in the USA and the European Telecommunication Standards Institute. Now, why do we have these, let's say, this many? Now think about telephone networks, like the mobile phones. See, the frequency is not free. Like you cannot send at any frequency you want, because let's say you have Etisalat and Du, for example, here. Now imagine Etisalat and Du, they work on the same frequency. So there will be some collisions, some interference between signals from both sides. So in this case, like there will be a lot of disagreement between these two companies. So there will be, there should be some authority or some organization to organize the frequencies that each company work on. So in here, you Du will work on a different frequency when compared to Etisalat. Otherwise, there will be a lot of problems, a lot of legal issues, and so on. So that is why in the, let's say, standards and policies has to be put to avoid any misagreements between companies. All right, now the physical components. So it's the responsibility of the physical layer to address these 3 functional areas. So we have the physical components, and that's going to be the focus of today's lecture. Then we have the encoding. It's a bit difficult topic, and this is the responsibility of the network layer. And the signaling, how to send the data. And this one we're going to cover it today, inshallah, by the frequency division multiplexing, time division multiplexing, and code division multiplexing. We will not go deep into encoding. Probably we're going to cover it later in the subject. Okay. So the transmission medium is actually the physical path between the transmitter and the receiver. So imagine this is that sender here. Imagine that you have the other 6 layers somewhere on top. So the physical layer will send the signal. It's going to travel through the medium. It's going to be either cable or air. It will be received by the physical layer of the receiver and then proceed for processing. So the transmission medium, or the transmission medium, is located below the physical layer and controlled by the physical layer. So this is the job of the physical layer, is to control the, let's say, what kind of signals that go through the transmission medium. Okay, so this slide here kind of summarizes a graphical representation of the media. And notice here in the unguided, we put everything in free space because that's the transmission medium there. Though we have 3 types, we have microwaves and radio waves and infrared. Now in the guided, we have twisted pair, coaxial, and fiber optic. So let's start with the twisted pair. So the twisted pair consists of 2 insulated copper wires. So keep that in mind. That's a typical question you will face in the exam. What is the material of twisted pair wires? It's copper wires. And they are, let's say, connected in a regular spiral pattern. Now, why they do the spiral pattern is more into for noise cancellation and to reduce interference from other wires. So a wire pair acts as a single communication link. So each pair is a single link. So it's either sends or receives. It does not do both. Even though it's 2 wires, they work as a single link. Keep that in mind. Twisted to reduce electrical interference from similar pairs close by. And the more twisted the wires, the better the quality is. So that's a typical short answer question or an essay question. Why do we do twisted pairs? Why don't we have them as straight lines? to reduce electrical interference from other wires or other pairs. Now, a typical application for twisted pairs, the telephone networks between house and local exchange, and the LAN. Basically, a typical application for twisted pairs is the RJ45. It's the Ethernet cable, the one that we see every day, the Ethernet cable. That if you go to the DO box or Etisalat box, you will see the Ethernet cable coming out of the modem to the router. So here's an example about the difference. So in this case here, we have a twist length of 7.5 centimeter to 10 centimeter. So there is kind of relaxed, they are not very tight. Now in this one here, if the twist length is 0.6 centimeter, then it's kind of connected, like strictly tight to each other. So this is a category 3 and this is a category 5. Like just changing the twist length, change the category. Now each category has difference among the other. We will not go into deep details about these categories. Now UTP is unshielded twisted pair. We'll cover that later, inshallah. So here is an example. Now when you have just a plastic cover over the two wires or over the pair, we call it unshielded twisted pair. Now, when you have a plastic cover and you have a metal shield over the wires, this is what we call shielded twisted pair. Now, the shielded twisted pair has more advantage because of the metal shield. You will have less interference from other pairs and you will have better quality. However, think about it, you have metal here, so it will be heavier, it will be harder to control and harder to carry, harder to handle. So this is like the difference between shielded and unshielded twisted pairs. Okay. Now the cabling. So we have category 3. It was originally used for voice communication over voice lines, but later used for data transmission. So this is the category 3. Now here notice like it's not very, they are not twisted. They're not very twisted. And they're represented by a straight line, but they are twisted pairs. And it's unshielded, all of them are unshielded twisted pair. Now this one, if you were asked, category 3 was used for voice communications. Pretty much like for telephone calls. Now, used for data transmission, that was back in the day when we had the dial-up connection. I think nowadays they don't do that anymore. So the dial-up connection, like in the late 90s, early 2000s, we used to use the phone to connect to the internet. We didn't have this Ethernet technology yet. Then category 5 and 5E, it was used for data transmission. It supports up to 100 megabit per second, and 5E supports up to 1000 megabit per second. And this is pretty much what the Ethernet connection. This is Cat5, and you'll see that if you go search over the internet, you will see that Cat5 is more into the RJ45 or what you call the Ethernet cables. Now, category 6 has added a separator between each wire pair to support higher speeds. Again, when you have more insulator, like a wire in this case, you will have less interference between two pairs. So when they added separator between each pair, it supports higher speeds. Now here it supports up to 10 gigabit per second. Then we have category 7, 10 gigabit per second. Category 8 support 4 gigabit per second. So it's easy. There is no even numbers except for 6 and 8. So it starts from 3. Telephone calls, dial-up connection. Category 5 and 5E, that's the Ethernet cables. Cat 6, it's an improvement to 5. They just added shielded wire. Each pair is shielded. So you'll have less interference. You'll have higher speed. 7 and 8, you just more speed in there. Okay, so here is like an example of how twisted pair look like. The Ethernet cable consists of this, exactly the same thing. So you'll have this cable here as a support, and you have the pairs are here. Okay. So here's a comparison between unshielded twisted pair and shielded twisted pair. So unshielded used for telephone wires is cheaper because there's no metal. It's easier to be installed and handled. Again, there's no wire, it's easier to deal with. But because of the lack of insulation or support from the metal coating here, or the metal cover, it suffers from external electromagnetic interference from other pairs. Like this pair here could interfere with this pair here, and that will reduce the performance. Now for the shielded twisted pair, so there is a metal braid covering the pairs to reduce the interference. It is more expensive because you have more material, you have metal inside the cable, and it's harder to handle. It's thicker and heavy because of the metal coating here, or the metal cover. So here's a quick comparison between unshielded twisted pair and shielded twisted pair. So are we okay up till now in the twisted pairs connection? Make sure it consists of copper. Typical application is telephone connections, Ethernet connections. We have shielded and unshielded. Shielded is better, but more expensive and harder to deal with. Okay, so here's an example here. So this is like the socket, what you see on the wall. And the pair connection are like this. So this is 1 and 2, they are a pair. 3 and 6, they are a pair. 4 and 5, a pair. And 7 and 8, they are also a pair. And this is what you have from the cable or from the wire, you put it on the wall. And yeah, this is what we see in real life. Now for the cabling, there are 2 ways to connect.
دكتور
Yes.
again can you go back to the last slide? Can you re-explain لأنه ما فهم دكتور أحاول أفهم.
No, this one here, like this is like what you see in real life. Like if you go to the
1 2 3 4 RAS 5 6
okay. Now in the twisted pair here, you see one, like you have 1 pair here, another pair, another pair. So you have 4 pairs.
Yes.
So that makes it 8 wires.
The 8 wires.
Exactly. Now if you go here, you have 8 connections.
Oh.
You
Okay.
see?
Okay. Yes.
Now let's assume this is 1 and 2. This is the pair. So 1 and 2, they should be connected here. Now, assuming like this is a pair here. So this pair should be connected in 3 and 6.
Okay.
Now this pair here, 4 and 5. Like so for each 2 pins here or 2 digits, it's a pair. So 4 and 5, they are a pair. 3 and 6, they are a pair. 1 and 2. So this is just the labeling for this device. But here are the pairs, and this is the way you connect them.
Okay. Okay.
All right. Okay, so for the cabling, how to do that? By the way, we have 4 pairs here, but 2 pairs will be unused and 2 pairs will be used. So yeah, keep that in mind. So we have 4 pairs, 2 pairs will be unused. That's for Ethernet connection. Now, how to do the connection? Now, there's 2 technologies or 2 methods. So there is a straight through cabling and there is the crossover cabling. Now, what is the difference? If you want to connect different devices, and by different device, like different categories. So let's say from PC to a switch or hub, use straight through a cable. From router to switch or hub, straight through cable. But if you want to connect from PC to PC, it has to be crossover cable. Hub to hub, switch to switch. So if it's from similar component to a similar component, you use crossover cabling. If you connect different components or different communication components or end users, you will use straight through cabling. Now, how to do the connection? Now, remember, we have 1 and 2, they are a pair. So 1 to 1, 2 to 2. Like how to do that? Let's see, like we have these numbers here and we have these numbers here. So if I want to connect from my computer to the Ethernet, I will use the straight through cabling. And how to do that? 1 and 2, they will be like, it's going to be the straight through cabling. 1 to 1, 2 to 2, direct. And the pairs 3 and 6. So go here, 3 and 6 will go directly to 3 and 6 here. So remember, this is like what we call the female connection, and here's the male connection. So it's going to be direct, and that's the straight through cabling. But if I have to connect two devices, like two similar devices, I will do the crossover cabling. So the crossover cabling, I'll connect 1 to 3. How to do that? Like here in the connections, in the wire, like 3 here. The wire that will be, let's say, to it, that will be from another pair. That will not be exactly the same as the straight through. So it goes back to the connections here, how to do the connections. So the crossover cabling will be for similar devices, straight through cabling for different devices. So another one to summarize it. So here's like if you have a router to a switch or different devices. So unlike devices use straight through, like devices use crossover. So keep that in mind. How to do that? Again, you have when you put the pairs inside this part here, like you have the color conventions. So assuming this is the pair number 1, the blue, and the green one is another pair, the brown one, the third pair, the orange one is the third pair. So you do the connections based on that. Take into account if you are connecting different or unlike devices or similar devices to play with the connections. Yeah, I wish if we have access to, let's say, to the campus, I would have shown you how to do that like in real life. But I don't have the components here in my home. All right. Or we can look, I will look into a video on YouTube and send it to you, like how to do the straight through and crossover cabling. All right. So I believe that's it for the twisted pairs. Any questions on the twisted pair connections? Any questions?
No, doctor, they are clear.
All right, inshallah. Okay, so let's keep going. Now we have the coaxial cable. Coaxial cable is kind of limited into applications. Back in the day, let's say satellite dishes and so on, well, like this is the cable that carries the signal. So it consists of external coat, that's a plastic coat. So we have copper wire, braid or foil, and you have the conductor here. And one thing, like this wire, the copper wire should never connect to this conductor. Otherwise, it will be a shortage and might damage the device. Typical applications in TV connections or TV cables. That's a TV cable. I'm sure that you guys have seen it somewhere. Now there are too many categories for this coaxial cable. So there's the RG59, that's the cable TV. Now RG59, that's a thin Ethernet, thin base 2, and RG11, that's a thick Ethernet. In some applications, let's say for example in the United States, I connected my house through this one. Like they did not have the Ethernet cable there, but they have this one. So I plug in the router into the wall, and it had something like this. So it was a coaxial cable, and it gives internet. So these are the applications for this one. But the most widely used one is the cable TV. But nowadays, nobody has it. New technologies now, we have the IPTV, that, the eLife and the DoBox and so on. So this is the only application for coaxial cables, it's cable TV. And there's not much to talk about it. So yeah, that's it about coaxial cables. So coaxial cable, if you want to summarize it, it has these 3 components: an external coat, a copper wire, a braid or foil, and you have a conductor. And there is an insulator type material here. Okay, fiber optics. It consists of 3 concentric sections. So we have the plastic jacket here for protection for sure, and you have glass or plastic cover. Usually it's glass, and you have the fiber core and cladding. The core is once inside, the cladding is like at the edges or at the sides. Now, the core consists of 1 or more very thin strands of fibers made of glass or plastic. One key concept here in twisted pairs, the signals we send is electric signals. Now, in fiber optics, the signal is light. So the source of the signal is an LED, a light emitting diode. So this is the difference between optical fiber and electric signal, twisted pairs. Twisted pairs, the signals are electric. And here the signal is light. So it consists of 1 or more very thin strands of fibers made of glass Now, each fiber is surrounded by its own cladding. So this is like what we have here, the fiber, the core, and the cladding on the side. So it's the one that's covering the core. Now, a glass or plastic coating, that is a different type of the core. It has to have a different properties or optical properties from the core, because it goes back to the science of critical angle in order to have the light fully reflected. Because here the signal is the light reflected over the edges. So you need to have different mediums in order for the light to be reflected. Then we have the jacket. It's a plastic or other material that acts as a layer for protection. So here's the jacket, just for protection against moisture, crushing, and other environmental dangers. And there you go. This is the key concept here. So here's the sender. That's an LED, light emitting diode. It sends light. And there you go. The light is reflecting inside the core until the receiver receive it. And there you go. The signal is there. Now, what are the advantages of fiber optics? Greater capacity. By capacity here, it's going to be speed. So data rates of hundreds of gigabit per second. And you have seen nowadays, like when somebody brags that he connected to a fiber, he got a fiber cable and so on, he will get a higher speed, better quality. And smaller size and weight when compared to the copper wire, because that is copper, so it's metal. So here is the smaller size and weight, and lower attenuation, signal loss. So because of lower attenuation, the signal will not be lost, or great repeater spacing. You guys remember what the repeater is? It's a signal amplifier. Now, because I don't have attenuation, I'm not losing a signal, so I don't need a lot of repeaters. So every tens of kilometers, I need one repeater. Now, no crosstalk, no light leaking. Light leaking, again, because the signal is light. So because I'm having the core and the cladding, the light will be perfectly reflected, so I'm not losing any light. Electromagnetic isolation, basically because my signal is light, is not electric signal. In twisted pairs, since the signal transmitted in twisted pairs is electric, there will be an issue there. There will be interference from the environment. In here, the signal is light. So there will be no electromagnetic isolation, there will be no electromagnetic interference. And it's highly secure, again, no light leaking. Now, why we call it highly secure? Because the signal is within the light. The information is within the light. So if there is some light leaking, that means that information are going out. But because the light is not leaking, there's no light going out, so it's highly secure. So those are the advantages of fiber optic. Now, the disadvantages, it's not easy to install and maintain, and you have to be careful with that. Also because it's made of glass. Glass could be broken. Unidirectional. So in order to have a communication channel, you need two fibers to, let's say, get a bidirectional connection. By that, we mean like one fiber for sending and one fiber for receiving. So each fiber cable is unidirectional device. If I want to get a bidirectional, I need two fibers. And the cost is more expensive because interfaces than electrical interface used with other types. When compared to twisted and coaxial, it is expensive. Okay. Nowadays, fiber optics is widely used, but it's mainly used in four types of industry. Now, enterprise networks. So it is the backbone cabling for interconnecting infrastructure devices in enterprise networks. Fiber to the home. I'm sure you guys heard about it. That's what you get with a very high speed internet. So it's used to provide always on broadband services to homes and small businesses that you're getting a higher speed of internet. Long haul networks used by service providers to connect countries and cities. And you have submarine cable networks. And it's used to provide a reliable, high-speed, high-capacity solution capable of surviving in harsh undersea environments and up to transoceanic distances. Now, if you want to search the internet, submarine cables, telegraphy map to view various maps online. So this one just to connect, over the sea. Like there will be, like, you know what submarine is, like it's under the sea. So there are very large cables connected areas and probably continents over the, let's say, the world. So these are like typical applications of fiber optics, and that's their usage. I think the most widely used ones, so we're going to talk about the enterprise and fiber to home, because that's, let's say, what we see in real life. Those, the other list, like we hear about them, and they are, let's say, at a larger scale. They are not just customer kind of connections. All right, so fiber optics. So let's talk about the advantages of each one of them. Fiber optics is immune to electrical noise, less signal attenuation, and higher bandwidth. Now, copper is lower in cost, less expertise, equipment needed, it's not complicated, and it's not easily broken when compared to the fiber optic. So this slide describes the advantage of each connection. Here, I did not include the coaxial cable. As I mentioned, coaxial cable is limited in application, and it's more into just cable TV. All right. Another comparison here between fiber and copper. Now, the band supported in unshielded twisted cable, pair cable is up to, let's say, it goes from 10 megabit per second to 10 gigabit per second, while the fiber optics can reach 100 gigabit per second. The distance is relatively short, like 1 to 100 meters, while the fiber optic can go to 100,000 meters. Now, immunity to electromagnetic interference and radio frequency interference. So UTP cabling is low, is not very immune. It could be affected, while the fiber optic is completely immune because my signal is light. So it doesn't matter like there are any electromagnetic signals or not. Electrical hazards. Here, sometimes you get shortage. You will get some issues with the voltage and currents. So it's not very immune. While the fiber optic, again, for the same reason, it's completely immune. Now, on media and connector costs, the cost is low because here just copper wires, while here you have to have glass and it has to be let's say clean and glazed and so on. So it is high expensive. Installation skills, you don't need skills. You just connect wires. And here it's a bit hard. It's not straightforward. Now, safety precautions, again, there is no need to worry about the connections and the safety as long as the power is low. While in this one, safety precautions must be high because, again, you are dealing with glass and that might harm skin. And I believe that's it. That's all about the guided, let's say, medium. Any questions about this topic? Any questions about the guided medium? All right. I think we are on a good pace. So we still have the guided medium and the signaling part. Now, unguided media. So these are signals that transmitted through air, and they are available to everyone who has a device that can receive them, like telephone networks nowadays. As long as you have a telephone, you can receive a signal. So it is divided into 3 categories: radio wave, microwave. Usually they are combined together, and you have the infrared. And right after the infrared, we have the light wave. Okay, so here just a matter for mentioning. You don't have to worry about this slide. So we have different bands, depends on the range of frequency. So we have very low frequency VLF, and this range is like 3 to 30 kilohertz, and that's usually for long range radio navigation. So it's not for like more into radars. Now low frequencies, 30 to 300 kilohertz. So radio beacons and the navigational locators, again, pretty much similar to the previous one. And the propagation has like, it's within the ground area. So there should be some line of sight. Now for the middle frequency, 300 kilohertz to 3 megahertz, that is the sky. That's the AM radio signals. AM is amplitude modulation. So that's for air. Like if you go to radio channels, I believe this is going to be the range of frequencies in there. Now in high frequency from 3 to 30 megahertz, so that's what we call a citizen band, ship aircraft communication. So usually aircrafts, they communicate within this range. Then there is the very high frequency, 30 to 300 megahertz. This is like the FM radio. Now, if you go to the radio and you realize most of the signals here are from 85 kilo to 85 megahertz into 110 megahertz. So yeah, that's pretty much like for the FM radio and the TV, but I don't think people use very high frequency TVs anymore. Ultra high frequencies, now in here, it's line of sight, pretty much like the cellular phones, paging, satellite. 3 to 30 gigahertz, that's the super high frequency for satellite communications. And then here, the extremely high frequencies are for the radar and satellite. So that's it. Again, this is just for the sake of review, that for the different range of frequencies, you will get different application. Okay, so let's talk a little bit about radio waves. The range is from 30 megahertz to 1 gigahertz. First of all, it's omnidirectional. By omnidirectional means that it goes by one direction to all. So it's like a broadcast. So signal propagates in all directions. Now, easily interfere with other signals sent at the same frequency range. Like the radio signals nowadays, like you have seen that in, let's say you have your radio on in the car and you went to somewhere a little bit far away. Like this, you will notice like some signals start to interfere with each other. So there will be some easily interference here. Can penetrate walls and can be received in the building. Well, yeah, like that's what you see in the car. So it penetrates the car boundaries. Does not require dish-shaped antennas. Again, if you think about radio waves, think about your radio device in your car. So there is no need for any dish-shaped antennas. And there is a broadcast radio, AM, FM, TM, TV, cordless phones, paging, cellular phones. So those are the typical applications for radio waves. And the range is 30 megahertz to 1 gigahertz. For this kind of slide, I suggest to memorize the frequency range, the type of signal. And in this one, as I mentioned, radio waves, remember the radio device in your car. And if I ask you like radio waves, they require dish-shaped antennas. That is definitely false. It's the opposite. It does not require that. So radio waves, to summarize it, used for multicast communications, such as radios, televisions, and paging systems. Now we have the microwaves. Microwaves go from 2 gigahertz to 300 gigahertz. Now they are highly directional, line of sight propagation, straight lines. And if there are any objects in between, it will, let's say the signal will be attenuated or stopped. They require dish-shaped antennas. They are point-to-point. By point-to-point, that like the sender and the receiver, they should be able to see each other. So the antennas, they should be aligned. It's very high frequency, but cannot penetrate walls. And that's a disadvantage, like if the receiver is inside the building. And that's why, like if you remember back in the day, the dish antennas has to be outside the building, just to receive the signal from the satellite. It is used in long distance telephone communications and the satellite TV, used for short point-to-point transmission between buildings to connect their LANs. That's kind of not applicable anymore. And it's widely used to wireless networks and satellite communication. I'll give you an example also, like in this one, if you stand in front of the satellite dish, you will lose the signal. Like I've done that back in the day at my home. Like if the satellite is going well and you receive a signal, just stand in front of the satellite, you will lose the signal. Because there should be a line of sight. It should be a straight line and there should be no obstacles between the sender and the receiver. So it's used for unicast communication. Unicast means it goes to a certain direction. So it's not broadcast like the radio frequency. And such cellular, telephone, satellite networks, and wireless LANs. Again, wireless LANs is not widely used anymore. Now the last part is infrared. Infrared, think about the remote control of your TV. There is an infrared device. So it has a very large bandwidth. but it's not completely utilized because of the lack of electronics technology. It's local, short distance communication is not for long. Again, remember the remote control for your TV. If you go to another building, it will not, it will not send a signal. Line of sight propagation, directional. You have to direct to the TV to receive the order. Use the local point-to-point transmission or multi-point within very limited area, like a single room. Use the remote control, infrared data associations, port like wireless keyboard, mouse, and so on. Cannot be used under the sun because of the interference with the sun infrared rays. So that's the key point there. The rates are very slow, 75 kilobit per second up to 8 meters. And that's it. That's about the infrared. It can be used for short range communications in a closed area using a line of sight propagation. So that's it about the guided media. The unguided media, sorry. So we have microwave signals, we have radio frequency, microwave frequency, and infrared. Radio frequency, think about the radio device in your car. Microwave, think about the dish antennas, the TV satellites, and infrared, the remote control of your TV. Now, what is wireless media in general? So it carries electromagnetic signals here, and they are represented in binary digits of data communication using radio or microwave frequencies. So the limitations for the wireless media, coverage area. Now, wireless data communication technologies work well in open environments. If you deal with big, let's say, cities with big obstacles and so on, you might get a loss on the signal. Interference. Now, because the medium here is air, anybody who has a receiver device can receive the signal. So wireless here is susceptible to interference and can be disrupted by such common devices as household cordless phones, sometimes fluorescent lights, microwave ovens, and other wireless communications. Now, security could be breached. Anybody can receive the signal. If they have the right device to decode the signal, they can get the information from there. So it requires no access to physical strand of media. Therefore, devices and users not authorized for access to the network can gain access, again, with the proper technology and device. Network security is a major component here when it comes to wireless network administration. Now, another issue is the shared medium. Like it's half duplex. We'll go to that later, inshallah. Full duplex, half duplex, and simplex. Half duplex means that you either send or receive, which means only one device can send or receive at a time. The wireless medium is shared amongst all wireless users. Many users accessing the WLAN simultaneously results in reduced bandwidth for each user. This one easily can be explained at your home. If you have many people using the Wi-Fi, you notice like the speed is dropped, and or let's say, or somebody is using the Wi-Fi to download the file. The others will realize that they cannot. They open YouTube, but the buffering is not very fast because it's shared medium. So those are the limitations of wireless medium. Now, there are many types of wireless media. And actually, the wireless media, the association or organization responsible for that is the IEEE. So there are different technologies. And IEEE 802, I believe, is the one responsible or more into wireless media in general or wireless standards. So 802.11, that's for the LAN. And that's for our Wi-Fi, home Wi-Fi, commonly used as referred to the Wi-Fi. Now, 802.15, so this is the wireless personal area network. This is the Bluetooth. Now, you know what Bluetooth is. Like you send the signal, but in lower speed, and it doesn't have very high range. It uses a device pairing process to communicate over distance from 200 meters, and is not very fast. And you need to do the device pairing. WiMAX, that's 16, commonly known as the word interoperability of microwave access. This wireless standard uses multi-point topology. Let's not worry about it. And there is the Zigbee. Zigbee is kind of an extension to Bluetooth. So it is used for low data rate, low power communications. It is intended for applications that require short range, low data rates, and long battery life. Typical application for Zigbee is an Internet of Things and smart houses and so on. For me, I would like to just focus on Wi-Fi and Bluetooth. Those are the widely or the commonly used ones, Wi-Fi and Bluetooth. And I believe that's it for the unguided media. I'm going to talk about in general about bandwidth. So what's the time? We still have 20 minutes. Now the bandwidth, higher bandwidth means higher speed. So different physical media support the transfer of bits at different rates. We have seen it previously now, gigabit per second, megabit per second, and so on. Now data transfer is usually discussed in terms of bits per second or the bandwidth. And it is like the definition of bandwidth is the capacity at which medium can carry data. Like think about it like a car, a bus, and a train. Something like that. A car has low capacity, it cannot carry many people. A bus can carry more people. A train can carry higher people or higher number of people. Now here, since our signals are digital, so we're going to deal with digital bandwidth in terms of bits per second. So yeah, there you go. Let's not go over this. I think we did that in the introduction chapter. The terminology for bandwidth here. Okay, so some terminology here. We have three key concepts or key definitions: latency, throughput, and goodput. Now, latency, it's the amount of time, including delays, for data to travel from one given point to another. Pretty much like, remember the ping command, it will give you like the time took to send the data. That's like the latency. So it's the overall time to send a signal from the source to the destination, and includes all delays. Like if there are any delays, it should be included. Now, throughput is the measure of transfer of bits across the media over a given period of time. Now here, the bits could be data bits, could be controlling bits, could be all kinds of information bits. Now throughput, so it's a measurement and it'll be over a period of time. So it'll be usually in bits per second. It's going to be like a unit of speed. Now goodput is similar to the throughput. However, here it's not all bits, it's the usable bits or the usable data. So it is used to assess the transfer of data, and it is like the measure of transfer of useful bits across the media. Remember, we have control bits. If you remember in the last lecture, we have the headers, tailors for each packet. So we start the data at certain size, then we add headers to it to send it. Now this will reduce the goodput because I'm only concerned about the actual data itself. The rest are control bits. They are fine. They help to send the signal, but still they will take part of the bandwidth. So those are the concepts. You just need to know the difference between each one of them. Now, latency is time. Throughput, goodput, they are more into speed because it is the amount of bit per time. All right. Signal transmission, we are almost done. Actually, we still have about 4 to 5 slides. Now we have time division multiplexing, frequency division multiplexing, and code division multiplexing, or multiple access, like in this one here. Now, you have multiple channels. They need to coexist. Again, think about the space. The frequencies are limited. Yeah, not everybody can use the frequency. So there should be a mean of managing the resources. So you can send at a different frequency or a different time or a different part of the space. Now, space can be limited using wires or using transmit power of wireless transmitters. So here the space is limited. Imagine that for each two computer connection, you need a cable. You'll end up with a lot of cables when you have a big corporate or a big company. Now, frequency multiplexing means that the different users use different part of the spectrum. So this is similar to the radio. You have channel X with a certain frequency, that's 95.5, and you have channel Y 102.5. So yeah, like let's say what makes radio FM or sorry, Star FM, for example, as let's say a different frequency than radio 1. So because of this, now they just divide the frequencies among them, and this is the job of the Authority of Telecommunications here in this country. And that's why each one of them, they divide the frequency among themselves. And control the time as a data link protocol issues. Like if you want to send, sorry, if you want to send at different times, because they are sharing the same wire, for example. So someone should manage the time to send the signal, and this is the job of the medium access control. And this is part of the data link layer or the data link protocol. We'll cover that later, inshallah, in the course. Okay, now let's talk about each one of them. Time division multiple access. So different users can use the wire at different times. So the overall signal will be an aggregate of all signals sent there. So let's say, for example, you have this is the chart here, sorry. This is the one here. So this is signal A, signal B, signal or source A, source B, source A. So you have two sources, A and B, and they are sharing the same communication wire. Now each one of them is taking a portion of time. Like it's like on-off switch. I say signal source A send the signal, then put an off. It allows source B to send the signal. Once source B sends its share off, now source A sends the signal, and so on. Now the issue here, you will need a higher bandwidth because the signal sent in the wire is overall signals from different sources. So in time division multiple access, different signals could be sent at different times, but you need higher bandwidth. And this figure here is just to show you that this is the original signal. Like if you are sending from one source, this is the whole signal. This is the bandwidth you need. But if you are doing time division multiple access, you will need higher frequency signal because you are sending from multiple sources. So that is time division multiple access. Now, in frequency division multiple access is a bit different. Now here, my axis here is the frequency. So here is signal source A, source B, source C, D, and so on. Now there are different contents. Each one of them occupies a part of the frequency. Again, the best way to understand the frequency division multiple access is think about the radio device in your car. Like each channel has its own frequency. And that's what happens here. So you share the bandwidth among multiple sources. Now, a quick comparison between them. Now, with frequency division multiplexing, different users use different part of the frequency spectrum. So pretty much like this. So this is source A, B, C, and D. Now these signals are used in the same time, by the way, but at different frequencies. So you have 4 different frequency bands in this one. Now each user can send all the time at a reduced rate, and like pretty much like roommates. Now with time division multiplexing, users can send at different times, like this one here. So this is source A, B, C, D. Now source A got to send the signal, B, C, D, and so on. So this whole thing of all sources together is called a frame. So each user can send at full speed, but for a limited amount of time. Like an example here, like a timeshare condo. The two solutions can be combined, but that's going to be complicated technology. Like here, the examples or the analogy, like roommates. Like imagine there are like you are in a room and you have 3 roommates. All of you can use the same room at the same time. But let's say you don't have all space to do what you want. Now, with time division multiplexing, the 3 guys, they are using the same room, but each time one is using the room, the rest will be outside. Timeshare condo. So this is the analogy for the comparison between time division and frequency division multiplexing. Now the third one, and that's the commonly used one, is the code division multiple access. Now, each user is given a code that is assigned to him. And this code sets the partitioning. Now, used mostly in wireless broadcast channel like cellular, satellite, and so on. Now, our phones nowadays, they use code division multiple access. All users, the same frequency and the same time, but there is a different code for each user or a chipping sequence to encode the data. So it allows multiple users to coexist and transmit simultaneously with minimum interference. And here just mentioning that the chipping codes has to be orthogonal. Let's not worry about orthogonal for now. Now, why code division multiple access? The best analogy to do that, imagining that you have two guys in a coffee shop and they speak in Arabic, for example. And let's assume the surrounding area, they all speak in Arabic. Now, these two guys has to speak louder because the Arabic language, the same code, they interfere with them. So there's interference with the same language. But let's assume the same scenario, two Arab guys, but now they are in Russia and that cafe full of Russians. Now, it doesn't matter what the other people say, nobody will pay attention because they use a language that's different, that is, we do not understand. So this is what code division multiple access, like you have someone speak in a language that's unique to himself. So nobody can interfere with his language. And this is the analogy for code division multiple access. Each one is given a code, and that code will allow his signal to be secured and there will be no interference from other sources. I believe that's it for this one, for the transmission medium. Just a quick wrap up. We have two categories. We have guided and unguided. In the guided, we had the twisted pairs, coaxial cables, and fiber optics. Each one of them has advantages over the other, so it depends on the design. The designer or the engineer select what he's going to use. Then we had the wireless. Wireless technologies are a bit complicated when compared to the guided media, but they have advantages over guided media that you don't need a physical medium. So there is radio frequency, microwaves, and infrared. Each one of them has advantage over the other.